Hello everyone, my name is Yu Konno from Ishinomaki Sensei University, Japan. My team Rogerio is going to present an application called Road Surface Condition Detection System. The team members are me and Makoto Sato. The supervisor is Professor Jun Mizuno. In this defense, I am the presenter and Makoto is the PPT operator. Dear drivers all over the world, during the winter season, when you go to work early in the morning by car, I guess everybody is worried whether the roads are frozen or not, like in this picture, right? Moreover, when you go back home late in the night on a highway, like in this picture, if the road is frozen, that's very scary, don't you think so? Your car may slip and even having a fatal accident. In order to avoid such traffic accidents, we have proposed a novel project called Road Surface Condition Detection System, which is mounted on a vehicle to detect a frozen road, as shown in this slide. Our idea is to use a MEMS micrometer mounted on a vehicle to scan a laser beam on a determined area, as shown with red lines. A CMOS sensor also mounted on the vehicle captures the images of the physical interaction characteristics between the laser and the road surface interface as shown with yellow area. One of the key points of this project is to give a sufficient time of 4 to 5 seconds to decelerate manually or automatically the vehicle speed. The measurement distance between the vehicle and the detection area is calculated by the product of current speed value and deceleration time. This procedure is continuously performed. In order to realize such a system, as shown in this slide, we designed and fabricated a vehicle model, which consists mainly of a two-axis MEMS micrometer, a laser tube, a CMOS sensor, an Arduino microcontroller board combined with a Raspberry Pi embedded computer. Potentiometer is used in place of vehicle accelerator pedal. Speakers are used for warning the driver with a beep sound in case of frozen road surface. The entire system implementation is shown in this slide. A handmade asphalt modeling the road surface is illuminated by the laser scanner mounted on the vehicle model. Image of scan area captured by a CMOS sensor also mounted in the vehicle model is displayed on the left side LCD monitor. A speedometer is displayed on the right side LCD monitor. As I explained in the previous slide, the speed is controlled by rotating the potentiometer, which models the vehicle accelerator pedal. The judgment of the road surface condition is done by the brightness image, which I will explain in details on the next slide. The principle of detection is as follows. A laser beam is scanned by a MEMS micrometer on a determined area of the road. The laser is diffusely reflected when the road is dried, as shown in the upper figure. Part of the light returns to the vehicle direction, thus a relatively high brightness image is captured by the CMOS sensor. On the other hand, the laser beam is peculiarly reflected when the road is frozen, as shown in the bottom figure. Almost no light is returned compared to that of diffused reflection case. Thus, the brightness image captured by the CMOS sensor is supposed to be extremely low. The reflectance of S and P polarized waves have been calculated based on the Cranor equations and plotted as shown in this slide. Whether the detector module would be mounted around the car roof mirror or bottom or front grille. Incident angles on the road surface will be around 87 degrees and 89 degrees at speed of 30 kilometers per hour and 100 kilometers per hour, respectively, for a sufficient warning time of 4 seconds. If only S polarized beam is irradiated, the reflectance at 30 kilometers per hour and 100 kilometers per hour will be around 78% and 92%, respectively. Those high reflectance values demonstrate that specular reflection can be achieved when the following conditions are fulfilled: irradiation of S-polarized wave and incident angle above 87 degrees. Experimental results of proposed detection system are shown in this slide. The micrometer has been driven near to the response frequency for both axes, so that a residual scanning has been performed. From these results, the detection principle has been verified. Detection result for dried road surface is shown in the left photograph. Diffuse reflection on the road can be seen by the CMOS sensor image. Detection result for frozen road surface is shown in the right photograph. Almost no returned light is observed, so that specular reflection can be verified by the CMOS sensor image. Since no time is left, I just display the conclusion in this slide. Thank you for your attention.
Okay, great. Yeah, we move to the question part. Yeah, please.
Thank you. Yeah. Oh, my video is off. Here's Ronald. One question. First, Luke has a hand.
Yes. So very interesting and innovative project. Now you're using the MEMS scanner to scan your laser on the road, and so as seen from the examples that you gave in the last slide, so I have the impression that you're scanning it on a rectangle, and you take that image with your camera. So it's not that the camera is directly following the speed of the laser scanning. So that was something that was confusing me. But in your images, I see that on the borders of your rectangle, also in the corners, that it is much more intense, the light. So what is the reason for that? So why is it not evenly distributed?
Okay, thank you for your question. So
if you use a mechanical scanner, maybe you can have these effects if you are not using a rotating mirror or something like that. But if you're using a MEMS mirror, yeah, then the speed is very high.
Okay, when the volume is turned to the right, the speed meters
So the intensity on the corners is, and on the side and on the right, for example, is much higher than in the middle. So I would expect if you use a very fast MEMS micro mirror that it would be equal, or what is wrong in my observation.
Using the polarization characteristics of the laser beam, it is determined whether or not the road surface is frozen, depending on the intensity of the brightness of the. Many times the laser repeats the corner.
Okay,
so
Yes.
that it's bright. Resadue
It's a
characteristic.
Lissajous. It's Lissajous image that you're making.
Yeah.
Okay, okay. So it's not simply a scanning like a television or something like that, or a scanning in one direction while you're driving, for example.
Okay.
Okay.
Other questions?
Yeah, one question: how do you distinguish between ice and water? So there might be as well water on the road, making the similar diffraction build.
Okay. It is our next matter. So we are researching the difference between the water and ice by we are researching the difference between the water and ice by change of reflective index.
Okay.
Did you double check the oil?
No.
Okay, I see. Any other questions? Okay, if not, yeah, let's thank all the speakers, all these 15 teams. Yeah, all the teams have done a wonderful job.